Hey, welcome guys. This is a video that I try to prove. I want to explain why E is transcendental. So I don't know where to fit this video, but I may put into the field theory or the Galois theory in the abstract algebra. Very interesting proof, and yeah, hope you guys subscribe to my channel. Yeah, so this problem proof E is transcendental. This problem is like a very old history, right? So let me just give it a quick definition. So when I say a number which is a transcendental, usually I'm saying over Q. So it means that if X is transcendental, there's no algebraic equations. So no algebraic equations or the polynomial over Q is set for 0. Let's say f belongs to Q of X and f is non-zero, such that f of X is 0. Okay. If there is a polynomial such that the Q of X is okay, so yeah, this is a transcendental. Okay, so if it's if you're talking about algebraic, conversely, if S is algebraic, that means that there is this f belongs to Q of X, and the f is non-zero, such that let me just use x0, such that f of x0 is 0. Okay, so for example, the square root 2 of 2 is algebraic because x squared minus 2 is 0. If for every non-zero polynomial that the x will not be the roots of it, then this is called a transcendental. Okay, so this is the definition. Okay. Yeah. So the famous results, let me just talk about stupid history. The famous result first is Hermite proof that I think it's once this. So E is transcendental. So where E is defined to be summation of 1 over n factorial and 0 from infinity, or basically, yeah, you can use the calculus limit. Okay, so I think it's this. Yeah, so this guy will not be any polynomial, any roots of the polynomial. And the second is that proving pi is a transcendental, which is more difficult. I think it's by Lindemann. Okay, so they say one is a okay, and a very simple exercise which I already proved in my other videos is that you can easily prove pi and e are irrationals. So basically, they do not belong to rationals. These are like trivial exercise. So I have a video about proving pi and e are rational, are irrational. I will post a link below if you want to see this. Okay, so proof e and pi are irrational are somehow like very easy step. Okay. So idea is that we want to prove that E is a much more difficult transcendental. By the way, so if let's say if somebody already proved that E is irrational, means that E cannot be written as A divided by B, right? So that means E will not be any roots of, let's say, AX minus B, or for every A, B belongs to rationals, except for A, B are both 0. Okay, so irrational is somehow like the first step that you prove that E will not be any roots of the degree 1 polynomial. So if you want to prove that E is transcendental, that prove irrational is somehow like the first step. Okay, so Starhouse theorem is transcendental. Okay, so proof need to satisfy some I qualify into different step, and I somehow try to skip this step and tell step by step, and finally we go back to the middle step and fill all the details. Okay, so let's talk about step 1. Okay, so step one is that let's write a theorem. Suppose f of x is a degree R polynomial, so degree of f is R. Basically, what I'm saying is that f of x just a r x r . Okay, and I use f of I of x means that the i's derivative. of f. Okay. Yeah. Okay. So I can define f of x. Let's say I define a capital F to be f plus f1, f2, up to fr. Okay. So you know that fr plus 1 is 0. Okay. So this you can easily check the following is true. Basically, d of dx, f of x. If you do it again, you get f1, right? So right. So this is you get f of 1, f of 2, f of r, right? So if you're working as an exponent d divided by dx, such an exponential negative x, f of x, you get that negative exponential x and f derivative plus what? Plus this and f. Okay, so which you can see that these two terms, if you take the exponential x, you get f prime minus f, you get negative f exponential minus x. Okay, so this is our theorem one. This is our first step. Okay, so first step is just this equality. Okay, so let's move to step 2. Okay, so step 2. So step 2 is a mean value theorem. Okay, so remember that if somebody give you like g of b minus g of a, there exists a g prime of c, right? G prime of c, which c belongs to a b. So I can write c as a plus a theta b minus a, right? So theta will be something in the 0 and 1. Okay, so it's a plus theta b minus a. Okay, so I want to use this theorem on our this equation, right? So I can get that let's say I choose a to be 0 and the b to be k. So I get the exponential negative k f of k. So k is some positive integer minus exponential 0 f of 0, and it becomes the derivative, right? So the derivative is a negative x minus f exponential x, right? So it's minus f, let's say theta k, right? So theta k times k. So I use theta k to label some point which theta depend on k. So theta k and there's a k here, right? And because this is k minus 0, and then there's also exponential derivative, right? So exponential negative theta k. Okay, so we got this. So which we have f of k minus exponential this is guys k f of 0 k exponential k 1 minus theta k f theta k minus sign. Okay. Okay. So let's write down. So remember this equation. So let's write down. So let's say I working on k from 1 to n. So I get f of 1 minus e f of 0 and f of 2 minus e f of 0. So sorry, e squared, because there's a k here. And then f of 3 minus e to the cube f of 0 up to f of n minus e to the n f of 0. And this guy become k is 1, right? So it's minus 1, minus 2, minus 3, up to minus n, and exponential 1 minus theta 1, f of theta 1, exponential 2, negative 2, 1 minus theta 2, right? Because right, so 1 minus theta 2, f of 2 theta 2, exponential 3, 1 minus theta 3, f of theta 3 times 3, the exponential n minus 1 minus theta n, f of n minus n times theta n. Okay, so you don't need to worry about this guy, right? Let's call it epsilon 1, epsilon 2, epsilon 3, epsilon n. Crazy enough. Okay, so let's prove. Suppose E is an algebraic number, right? So E is algebraic. So that means what? That means that you can find, let's say you can find Cn minus 1 up to C0. such that the Cn En C1 En minus 1 so C0 is 0, and for all C is rationals, and C0 is greater than 0, right? Okay, so this is the second step. Okay, so so this is the middle of second step. So we need to connect these to this. Okay, so the connection looks very tricky, right? So let's say if you times C1 for this equation and times C2 and times D3 up to Cn, right? Then you will see that this gives you minus C1, minus C2, minus D3, minus up to Cn. Okay, so you can combine all these, then it becomes 0, right? So finally, you will arrive at the following. You will arrive at C0 F0, C1 F1, Cn F of n will give you C1 epsilon 1, C2 epsilon 2, Cn epsilon n. Okay, so this is our step 2. Okay, so our step 2 basically combine the step 1 and step 2. Basically, somebody give you a degree R polynomials, and once you construct this capital F, and once you construct this capital F, then you can use the mean value theorem and prove that suppose E is algebraic. Then you can find you can, for every polynomial, this equation will be true. So the remaining is to find some polynomial, right? From polynomial F, which is weird, such that this equation will not hold. This is very weird. How do we find such equation, such polynomial F? Okay. So this is the previous smart guy which heard my finding. Okay. So step 3. So her might find what? Her might find F. Let's define F of X to be 1 minus P minus 1 factorial, P minus 1, X, P minus 1, 1 minus X, P, 2 minus XP, up to N minus XP. So P is some prime number. Okay, and P should be very large. Okay. Okay, so you can ignore expansion of F of X. So who is the leading order, right? So you got XP, 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 and then you have NXP, right? So the leading order will be not leading order. Oh, what is the smallest order? A smallest order is 1 times 2 times n, right? So smallest order must be n factorial. N factorial p minus 1 factorial x to the p minus 1, and there's this is the first term, and then you get second term, which is a0 xp p minus 1 factorial, and a1 xp plus 1 p minus 1 factorial, right? Because the smallest term comes from each polynomial given a constant, right? So it's 1 up to n. So this is the term. Okay. Okay, so let me just write down a lemma. This lemma I'm going to skip, and you just believe this is true, and then we go back, and then once we have this, then we go back to proof. We go back to prove that this is true. Okay, so lemma. Okay, so lemma is that if you define f to be this, then remember we get our lovely capital F, right? So lemma tells me that the f of 0 is an integer. It's integer, but p do not divide f0. Okay, and f of j is an integer, but p divides f of j for j equals to 1, 2, 3 up to n. Okay, so this is the tricky part that I will go back to prove. So start from here, you just believe me, this is true. Okay, so very, very weird that if you define a small f, then f0 up to fj will be integer. Okay. So step 4. Okay. So remember, due to this lemma, right? Due to this lovely lemma, I can do the C0, I can see that C0, C1, F1 up to Cn, Fn. So originally, I can say these guys are all rationals, right? But I can take out their common denominator, right? So make these guys every becomes integer. So C0 is non-zero, right? So this guy is not divisible by P because P divides everything, right? But not this guy. So this guy is not divisible by P. So which that P do not divide C1 epsilon 1 up to Cn epsilon 1. Okay. Okay, so now now here comes the proof. Here comes the tricky part. Okay, so we want to. So this is our conclusion. My conclusion is that I mean I always find some smart large enough P or whatever P, which this is true. Okay. So let's do something. So let's consider this epsilon I, right? So epsilon I, remember is what? So epsilon I is minus I exponential I1 minus theta 1. By the way, this I is some integer. It's not imaginary. Pure notation. I f of I theta I, right? So this is our theta I. So we just plug it in, right? So we can plug in, we get this 1 minus theta I to the P, right? So and the 2 minus theta I to the P up to n minus I theta I to the P minus 1. And then there's an I here and a negative I. And the exponential divide. So this is F, right? Divided by P minus 1 factorial. Okay, if you take absolute value, then what will you get? Okay. Okay, so if you take exponent, let's maybe, let me just delete here. So that we can just, we don't have to go to another page, but we can just bound this guy trivial. Okay, so this what is this? So this guy is bounded by what? So this theta I, right? So theta I is from 0 and 1, right? So now I can bound this by n factorial, right? So I get I and the n factorial to the power P and P minus 1 factorial and the exponential I, right? So I can choose I largest I to be n, right? So I get exponential n. And I don't care about this I, right? I can just choose it to be n. And oh sorry. I forgot a term which is I theta 1 P minus 1. Right. So if contains this term, then you can just replace I to be n, right? So it's n P minus 1. And yeah, so I think there's I here. So right, combine these two, you get n to a P. Okay, so yeah, this is just this term, which comes from the definition, right? You get xp minus 1. So you get this. And then there's a remaining I come from here. Okay, but don't worry, however, right? So your result will be epsilon I is bounded by e to n to the p, n factorial to the p, p minus 1 factorial. Actually, you don't care about this one. The only thing you need to know is that if p large enough, this guy goes to 0. Okay, so you can prove by L'Hopital because p factorial greater than any fixed power. Okay, so if you choose n to be whatever, right? Let's say your beginning n to be 100, whatever. I mean, if p large enough, this guy becomes 0. Okay, for every I. So we have trouble, right? Trouble because if p large enough, then each epsilon I will be less or equal to 0. Right, but the problem is that I know that epsilon I is what? The epsilon I will be integer by our previous lemma. sorry, I know that this guy will be integer, right? So which, if I bound this guy, this guy is bounded by, let's say, C1, epsilon 1, Cn epsilon 1. And then this guy, and then this guy, every epsilon cannot be arbitrarily small by choose large enough p. Right, so this guy is bounded by 0, and this guy is integer. So we proved that C1 F0, C2 F. Sorry, we proved that C0 F0, C1 F1 up to Cn Fn is 0. Okay, the reason is that the epsilon I can be arbitrarily small, right? Epsilon I can be arbitrarily small, and the right hand side must be integer. So if the absolute value of the integer is arbitrarily small, then it must be 0. Okay, contradiction. Because if this guy is 0, then what? Then each integer. Sorry, this is, yeah. So this guy is 0. So p will divide this integer, but we prove that p will not divide. Contradiction. Okay. So E is transcendental. Yeah, this is a proof. Okay. So let's go back to prove this lemma. Okay, so this lemma is the remaining part. You can do it like exercise, but I think the X is a little bit tricky. So let me just try to prove it. Let me just try to put it. Let me just write down my f of x, and again, and let's try to prove the lemma. So now we already get an answer, right? So hopefully, prove the lemma is not so difficult. Okay, so let's try to prove that that's the first part. Okay, so notice what? Notice that if I greater than equal to p. Oh, remember this guy can be written as the first term is x p minus 1 a0 xp p minus 1 factorial plus a1 xp plus 1 p minus 1 factorial. Sorry, p plus 1 and then something p plus 2 p minus 1 factorial and keep going. Okay, so if I greater or equal to p, and then we notice that f of I of x, right, is a polynomial. It's a polynomial, and since you do the differentiation more than p times, so every p minus 1 factorial will cancel. So f of I of x will be some integer polynomial, right? And each component, each coefficient is divisible by p, right? Because p minus 1 factorial cancel all this, right? So which means that f of I, let's say, yeah. So not each coefficient is multiplied by p, right? So h of ix, each coefficient is divisible by p, Okay, so since it's divisible by p, right? So that means what? That means that if you put j from, let's fix j from 1 to 2 up to n, right? So your fi derivative j will be integer, that divided by p. Okay, so now let's consider f of j, right? So our goal is to prove first element is to prove that j from 1 to 2 to n, these guys are integer and divisible by p. How to prove it? Okay, so let me just write down what f of j, right? F of j is f of j, f of derivative j, f of 2 derivative j, up to f of r derivative j, right? And this r is very large, right? So in this case, this R is x whatever p, right? Maybe x n p, right? So very large. You don't need to care, right? So notice that if this f of j has multiplicity p, right? So if you put f of j, you get 0, right, for 1 to n. And if you do a differentiation, you still get 0, right? Because each factor has multiplicity p, right? So each factor from 1 to n has multiplicity p. So which means what? Means that f of I j is 0 if I less than p, right? Because it still needs it has a multiplicity p. So if you differentiate less than p times, you plug s equals to 2, let's say 2, you get 0. Okay, so which proves that f of j is only survive when I greater than p, right? So you get proof. Right, but this guy, each of these guys is divisible by p, so f of j is divisible by p. So p divides f of j for every j from 1 to 2 up to n. Okay, so this is the first part that we just go to previous. So we just prove this. Okay, so let's prove f of 0 is an integer, but p do not divide f of 0. Hopefully this is easy to see. Okay, so remember this is our this. Okay. Okay, so f of 0. So we know that one. I know that f of x has 0. Has 0 has p minus 1 multiplicity, right? Because f of x, the previous f of x looks like this. So x of p minus 1. Sorry, I just stupid. I read again, right? So this is 1. So x p minus 1 has no as p minus 1 multiplicity, right? So so it means what? It means that if you divide less than p minus 1 time, then you get 0. If you put 0, so that means this means that f of I of 0 is 0 if I less than p minus 1. Okay. Okay. So and also the same thing happened, right? So I greater or equal to p, you get the f of I 0 is a still integer. And the multiplicity and it's the same thing, right? Because we proved that if I greater or equal to p, fi of x is a polynomial which each coefficient is multiplied by p. So this guy is divisible by p, right? Okay, but how? So there's a one term which we forget about here, which is I equals to p minus 1. Okay, so if I equals to p minus 1, let's suppose you differentiate p times, then this guy will cancel everything, right? Right? And if you differentiate by p times, you will see that if it remains n factorial. Okay, so if I equals to p minus 1, then you can easily say that f of p minus 1, 0 is n factorial times p. Okay, and yeah, that's it. And okay, and yeah, so f of p minus 1, 0 is n factorial to a power of p. Okay, so I can choose. So I can choose. I can just choose p greater than n. Then I can choose p greater than n, right? So n factorial will not contain p. So we show that p do not divide f of p minus 1, 0. Okay, so that means what? That means f of 0 is f of p minus 1, 0, f of p 0, everything is divisible by p here, but these guys do not divisible by p. So p do not divide f of 0 for p greater than n. Yeah, so yeah, previously, so actually I made a small mistake on this lemma. So this lemma need to require p greater than n. Okay, but yeah, this is a proof. So you might worry that why this is true if we made this a little bit change, but it's still the same, right? Because suppose you find some algebraic number, algebraic equation, right? Suppose you find some algebraic equation which has some particular n, then I can find the prime power. I can find some prime p which is larger than n. So I can find large enough p greater than n, right? And the lemma works. So the theorem works. So there's no way that you can make E to be algebraic. If you find any polynomial which satisfies this, then you will have some particular n, and I can find large enough p such that we still get our conclusion. So proof is just this. Yeah, so E is a transcendental. Okay, and there's a quick exercise. Let me just say some quick exercise which is also interesting. You can try to prove that E m divided by n, which mn is some integer, and should not be 0, is a transcendental. Transcendental. Okay, so yeah, this is also interesting proof. Yeah, let me just quickly say how to prove this. Yeah. Okay. So let me just try to prove it. I just feel a little bit lazy. Yeah. So the idea is that we want to prove that E m divided by n is a transcendental, right? So let's prove this. This is a little bit difficult. Let's prove some easy one. So let's prove the following lemma. So suppose x is a transcendental. So I use t, right? So suppose x is transcendental, and I want to prove that x inverse is transcendental. Okay, so this is very easy, right? Suppose x inverse is not transcendental, then I can find something which is a0 plus a1 x minus up to an x minus equal to 0, and a0 is non-zero. Then I can flip everything, right? And an also be non-zero, right? The smallest one I can flip, so I get that. So I get this. And this will violate the x is a transcendental. Okay, so I only need to assume that m divided by n is greater than 0. Okay. So let's consider the following. So let's consider x is e. So I can assume that m and n are both greater than 0. Okay, so now I can concede. Now that I get x to the n is e to the n. Okay, so I want to prove that there is a contradiction. Okay, so suppose x is not transcendental. That means what? That means that that means x is algebraic. Okay, and you can easily prove that if x is algebraic, then s to the n is algebraic. Okay, so which proves that e to the m is algebraic. Okay, and this is the final work that you can prove that if m is algebraic, then that means you can write down equation, which means is ai e to the mi, which is, let's say, from 1 to, let's say, n is 0, right? But this is exactly the same as I from 0 to n, ai e to the mi, right? Is 0. So this violate is transcendental. So contradiction, right? So x must be transcendental. Yeah, so this is another quick exercise that we are not just proof that. So now we prove that what? We prove that not just E is irrational. We prove that E is E to the any rational power, unless this guy is 0, is a irrational. Yeah, so this is the proof. See you guys next video. Hope you guys subscribe so much.